the center. So minus j of omega over 2, right? And I have here these other two parts, so that give me cos of omega over 2. No, this is divided by 2. Okay. Alright? So everyone happy with this? So that giving me that. So now we have to plot out the phase and the magnitude. So, and we're going to do this. Oops. So this is going to be the magnitude, and this is the phase of h omega. And here is omega. And as we learned before, all we have to do is just go from minus pi to pi. Because everything else is going to be repeated. Minus pi to pi. So having that function there, the first thing I need to do is maybe going to plot out this cos of omega over 2. So cos of omega over 2, at omega equal to 0, what does it? It's a 1, right? It is equal to 1. And then at omega equal to, and then you're going to go down. And then when omega equal to 2, so equal to pi, so you go to plus 0. So it goes something like this. Okay, something like this. So that actually is always not just a real number, but it's always positive. Right? Because remember this thing here, it not just have to be a real, but a positive number. Right? So I have this. So in that case, that's simply the magnitude. And what is the phase? The phase is minus omega over 2. Right? So minus omega over 2, that means it would be having this line. When equal to 0, equal to 0, equal to pi would be pi over 2. So it would be something, the line like this. This is a line of minus omega over 2. Alright? So that is a filter. This filter here, that's the magnitude of the phase. This is a linear phase. It is linear phase, right? Because straight line, linear lines. So this is a good filter. It's a good filter in the sense that it can everything go through and it lays them the constant speed. Right? So I don't have a mess up problem. Now what is this filter is doing? Well, you see the signal when omega equal to 0, it can't go through. And then slowly decays. So at omega equal to pi, it rejected. Right? So let's see what the signal between these two, right? So when omega, so look at this signal, cos of omega n, this cos of omega n, right? This basic signal. Well, when omega equal to 0, what I have is just cos of 0, 0, 0, 0, 0, so it's just constant signal. Boom, 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 right? That. When omega equal to pi, what that signal would be? Boom, 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 right? Such as 1 minus 1, 1 minus 1, 1 minus 1. So something oscillates extremely fast. That is a high frequency. Where this thing here oscillates, well, it's a constant, very smooth signal. So what it's saying here is the signal coming in, the component is a smooth, go through. Where this kind of component get what out, get Q out, get filtered out. Right? Is that clear now? So this filter, now we see the frequency domain, we see something, what we would expect before is that it actually smooths out the signal because it preserves the low frequency and filter out the high frequency. Okay? So that's the message. Okay. Now that is a simple case. So now maybe I don't want to show the filter, but let's say I assume now, how about I assume that instead, okay, maybe I do another one here. That is important concept. Omega equal to the magnitude is time with E of J, and then the phase of H omega. Okay, and this is real and bigger than 0, right? Bigger than or equal to 0. You agree, right? This thing is real and bigger than or equal to 0. Now suppose, you see in this case I got this, many filter, actually I can tell you I have, if the filter is symmetric, so if you have something here and you have something the same, something here and then something here the same, you can really group them together, right? And if something pop out and something, a real number coming out here. Right? So suppose more general I have H of omega equal to A of omega times EJ of theta omega. I have this. And what I can have here is a real, and this thing here is a real. Oh, this obviously is real, right? But you see, I really cannot guarantee that, this I'm lucky. I'm lucky that this thing here is a positive, a real and greater than or equal to 0. But there's a case where this thing can dip. This part can go down to non-zero. So negative. Then this thing here, if that was the case, then I can write this thing here is also going to be equal to, in the case of negative, the equation here is I can write that as minus of A of omega. I do the minus, so I multiply this thing by minus 1. I multiply this by minus 1, then I have to multiply it by minus 1. Right? This is after that they give me the equation. Multiply it by minus 1. I put them in here is, okay, is EJ of theta omega plus pi. You agree that these two things are the same? Okay. So if that's the case, then now if you want to equalize this with that, then I can write now that the absolute value of omega now would be equal to A of omega if A omega is bigger than or equal to 0, and equal to minus A omega if A of omega less than 0. Okay, so that's the part. And in pan, the phase of H of omega will be equal to, well, in that case, then I can use this form, because real and positive. So that must be the phase. Right? That's the fact, right? Any complex number is uniquely represent a real non-negative number multiplied with this exponential. Right? Because that's just a polar coordinate system. In that case, this phase equal to theta of omega if A omega greater than or equal to 0, but this thing here is minus, no, this is phi omega plus pi L, if maybe else. Alright, so that's pretty clear now. Alright, so we have that, and maybe, alright, so we, in general, we have that, that's the filter we have. Now, I'm going back to the